All right, welcome ladies and gentlemen. You want your notes open to video number 3 in our opening stoichiometry unit. In this video, I'm going to be talking about particle diagrams with stoichiometry, and specifically, I'm going to really be focusing on limiting reactants with particle diagrams and stoichiometry, because this is sort of the fundamentals of a lot of our stoich stuff, and particle diagram interpretation is increasingly on the AP chemistry exam. The key to any particle diagram problem when you've been given a situation like this, where we have a reaction and then we sort of they show you a reaction vessel with particulate representations, is to count. Literally count. Always start by counting up. How much of each thing do you have? So based on the key, I have hydrogen and nitrogen in this flask. So H2 and N2, and I'm just literally going to count. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 hydrogen molecules. And then nitrogen, I got 1, 2, 3, 4, 5. I have 5 nitrogen molecules. So after you count, that's where you want to start to pay attention to the stoichiometry. Remember, stoichiometry is really the crux of it is the idea of mole ratios. And they gave us a balanced equation right here. 1 and 2, 3 H2s, 2 NH3s. So there is a 1 to 3 to 2 ratio here, 1 to 3 to 2. So 3 H2s to 1 N2. Those, again, that's coming from the balanced equation, coming from the coefficients. These are our mole ratios. And then if you notice, with the actual numbers that we do in fact have in this flask, 15 to 5, it's the same as the balanced stoichiometric ratio. What that means, if the ratios are the same, if the ratio between the balanced equation is identical to the ratio that you have in your particle diagram, is that everything will be used up. There is no limiting reactant because you have the perfect ratio. So then look, another sort of way of dealing with this is sort of showing this idea of a ratio with the particles themselves, i.e. 1 N2 needs to react with 3 H2. So what I'm going to do actually is draw a circle where I have 1 N2 reacting with 3 H2s. And then I'm sort of going to keep on doing that because I know that this circle represents essentially one reaction. So I can do that again here. Again, it's the 1 to 3, 1 N2 to 3 H2s. Maybe this guy will react with these 3, and this guy will react with these 3. And this guy will react with these 3. And then once I've done that and I've completed, essentially drawn as many circles as possible, then I see that everything gets used up because I have the correct stoichiometric ratio. And there's not going to be any leftovers of anything. There's no limiting reactant. And then the next bit, notice this picture is simply just the circling. Again, this 1 to 3, now to 2 ratio. I know that for every 1 N2 and 3 H2s, I'm going to make, because it's a 1 to 3 to 2, each one of these is going to become 2 NH3 molecules, right? 1 N2 to 3 H2s makes 2 NH3 molecules. So drawing that out, it's simply going to look like that, where each one of these guys, the 1 and 2 and the 3 H2s, becomes the 2 NH3s. So I can predict how much product I'm going to make if I have this 1 to 3 to 2 ratio, with the NH3, and this is, let's see, N2 and H2, if I have 5 of the nitrogens to 15 of the hydrogens, you can predict even before you see it that you're going to be making 10 of the ammonias, 10 of the NH3s. Looking at just another problem with this, well, again, what if you don't have a perfect ratio? So your particle diagram, you always want to start by counting things up. So we have the same equation here. But we have now a different particle diagram. So counting things up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. And I have 1, 2, 3, 4, 5 nitrogens. Again, we have a 1 to 3 to 2 ratio based on the stoichiometric coefficients. That has not changed. There's a couple different ways you can approach this problem because it's pretty obvious that the ratio that we have here is not the same as the correct 3 to 1 stoichiometric ratio of hydrogen to nitrogen. I'm going to kind of talk about both of them because they're all totally valid. And the first thing that you can do is basically take each number that you start with and then think about what you need with that number, i.e. 9 hydrogens. If we're basing this off of the 3 to 1 ratio, 9 hydrogens would need 3 nitrogens. Likewise, 5 nitrogens would need 15 hydrogens. If you're sort of taking each number separately or thinking about how much you need, notice that we do have this, right? We have that in the box, but we do not have 15 hydrogens. You don't have enough. What this is all pointing to is that you have too much N2 and not enough hydrogen, which is absolutely another way of saying that hydrogen is the limiting reactant. Hydrogen's going to run out first. So that's sort of one thing that you can do. Another thing that you can do that I sort of strongly recommend is to have the same circling idea of a 3 to 1 hydrogen to nitrogen ratio. Circle it until you've made as many circles as you can, and then look at what's left over. So I know that I need 1 nitrogen and 3 hydrogens. I know that I need, let's see, 1 nitrogen and 3 hydrogens, 1 nitrogen and 3 hydrogens. I've circled up as much as I can. But I look at then what remains. This is left over, this is left over. So that means that it's an excess. And because I don't have any hydrogen in excess, again, this is telling me that hydrogen is the limiting reactant, that hydrogen is what is going to control how much product you can make. So just taking this through, this idea of the circling, again, where we had our 9 hydrogens and our 5 nitrogens, each one of these complete circles will make 2 NH3s, again, the 1 to 3 to 2 ratio based on the coefficients. But these will be left over. They're still going to be in your container. They're not going anywhere. They just didn't get a chance to react because you didn't have enough hydrogen in your reaction. So what is the finished reaction container going to look like? Well, we're going to have 6 NH3s because, again, the hydrogen, limited it. So 9 hydrogens reacted with 3 nitrogens in order to make the 6 ammonias. But then I also have the leftover 2 N2s still there. So we'll be practicing a little bit with particle diagrams. I'd expect that particle diagram problems would be something that would be on the multiple choice section of the AP, but a more numbers-based calculation would be, for limiting reactant, would be something that would be on the free response. And we're going to roadmap some of those number-based calculation questions together.